Of course, this year we're celebrating a lot of interesting anniversaries. The introduction of the IBM PC, text adventure games, and so on. The other anniversary that's really big this year is the 75th anniversary of the Eniac. In a sense, 75 years ago, the world of computing as we know it was born. And the center of that world was Philadelphia. So it's not Boston, it's not Silicon Valley, it's right here. Now, the Eniac, of course, here's the famous picture of the Eniac that was taken as part of the press release. This particular, a lot of the versions of this picture you see are very darkened because they were sort of scanned from printing in the newspapers. But I actually came across an original copy of the print. And so this is it taken with my phone. Hence the glare at the top. But you can see a little more detail in this than you can in most copies of this picture. As you can see, it was quite a large machine. It was built at the University of Pennsylvania during World War II. And a lot of the design decisions were made with an eye towards, we want to get this built as fast as possible to help with the war. We know there are other ways of doing things. We know there are more advanced ways we want to investigate later. But to get something out initially, we're going to take kind of the approach that we know is going to be the simplest. And that's what we're going to kind of be focusing on today is how does that work and how do you program it? Now, there's another talk that will be coming up right after mine. The creators of this were John Mauchly and J. Presper Eckert. Bill Mauchly, John Mauchly's son, will be here at the 10 o'clock talk, and he will be talking about the history and the people behind it. So I'm going to talk about the programming, then he's going to talk about more of the history. So what does this machine actually do? So this is the structure of it. Each of those vertical panels we saw in the picture is one unit. There are a total of 40 such panels in the machine, each one 8 feet tall by 2 feet wide. So that interior space that you saw is 32 feet by 16 feet. We're going to focus our example of programming on the master programmer and the accumulators. But some of the demonstration I'm going to show you a little bit later will make use of the multiplier, the function tables, the card reader and punch. I don't think, nothing in what I'm going to show you actually uses the divider square rooter in this case. But in terms of learning how to program it, we're going to look a little bit, we're going to focus on the master programmer and the accumulators. Now, this machine was famous, or some might say infamous, for being hard to program. I'm not sure I agree with that. I actually find it kind of fun to program. But I'll let you judge for yourself by the time we get to the end of this. It is a very interesting and unusual machine in a lot of ways. Now, this is how the units are laid out. I don't expect you to actually be able to read all of this. But this is a top view of the machine. And that photograph we saw earlier is looking at it from the left, looking in. And I've got an exhibit over there that is a 1/10 scale model of it. And so you're welcome to come by and kind of crouch down and take a look from that same perspective as that photograph was taken. What I haven't done is brought in like some dolls to give you a sense of perspective. I need to get some like 7-inch dolls to put in the model. But these units right here, as you can see in the picture, they are a little bit taller than a person. So that gives you a sense of scale when you're looking at it. And these are the roll-around function units. Essentially, this is to dial in tables of constants. So if you needed a table of logarithms, for example, or more commonly, the functions that weren't analytical. You might need, for example, a table of the air resistance as a function of velocity. That's not a simple analytic function, especially as you get near the speed of sound. And so if you want to simulate an artillery shell, for example, you've got to factor in that air resistance. And these tables right here are where those constants were put. So that's the part of it that's these kind of roll-around units right here. They're just big arrays of switches. And then all of the electronics was along the outside of this. To give you a sense of the scale of the electronics, this had about 18,000 vacuum tubes. It was the most vacuum tubes ever built into one device up to that point in time, by far. In fact, when they proposed the project, and they actually had initially proposed a little bit more scaled down unit that was only going to have, I think, about 5,000 vacuum tubes. They got a lot of pushback from all of the experts who said there's no way it's going to ever run because there's going to be a tube burning out so fast you're never going to get a computation done. This isn't to talk about the hardware engineering of it, but I'll just kind of tell you quickly that basically they figured out ways of operating the tubes in such a way that they would tend to last longer, slightly lower filament voltage than they were rated for. All of the circuits were designed so that the tube's gain could vary over a factor of 2 or 3, and the circuit would still work. So as the tube was aging and it would tend to weaken, it would still work. Plus they had test procedures and maintenance techniques that would make the downtime less problematic. For example, everything was a plug-in unit. So if a digit went bad, you just pull that digit out, plug a good one in, and then you take the bad one to the bench and figure out which tube is it or what other component had gone bad. So it was a much more reliable machine than people expected. And as I said, it is somewhat infamous for being hard to program, but I'm not sure I entirely agree with that. Now, the reason a lot of people who are writing about this will say, oh, it must have been terribly hard to program because you didn't have a keyboard to type on, you had to program it with the wires and the switches. Except that's not really the programming. That's just how you deploy the program that you've created. You know, the programming is when you're sitting down with a piece of paper thinking about it. And that part of it is not all that different. Yes, deploying it with wires and switches as you walk around the machine, plugging in cables and setting switches, that's a bit different than typing your code. In fact, what they would often do is have a whole team of people in the room. And somebody would be sitting there with a piece of paper that had all of the connections and switch settings. And then they would call out a switch setting like, you know, Accumulator 3, Program 6, Operation Alpha. And then somebody would go over there and turn the switch to the alpha position. And you had this whole room of people doing that as you're just calling it out to get all the connections. Now, in terms of difficulty for the programmer, this next point of there being no bulk memory is really a bigger constraint. It's a much harder thing to have to program. To give you a sense of perspective, the only modifiable data are the accumulators, and there are 20 of them. So the way to think about this is write your program using no more than 20 variables. You can reuse variables for different purposes later, but you can't declare more than 20 variables. If you can write your program that way, then you can put it on the Eniac. Now, another unusual aspect of this machine was the computations were actually done in those same accumulators that stored the data. What happened was anytime an accumulator received a value, it got added to the current contents of the accumulator. And the bulk of the arithmetic was in that form. So many, many additions. Subtractions were performed simply by transmitting the complement of a number. So if you add that complement, you get a subtraction. As I mentioned in the other slide, there is a separate multiplier unit and a separate divider square rooter, but that was the whole thing. That was all you had to work with, really. It was a very parallel machine. This is something that the developers of it and the early people who had experience with it, one of the things they came away with was a machine needs to be for people to understand how. Now, even today, we kind of generally feel like serial is easier to program, but I think we've grown up a little bit and we can handle some parallelism. And we will do a little bit of that. This quote by Lemmer. He had done some number theoretic work on the machine in the summer of 1946. And it was based on prime numbers. And so essentially he was going through finding a bunch of primes and then testing the characteristics of these primes to see if he could find certain primes that met these characteristics. And the way he generated the set of primes was by doing basically the sieve veritasenes. Only he tested all of the possible prime divisors in parallel. So it would test a number for primeness in one step. Very impressive piece of work. And as he said, it was a highly parallel machine until von Neumann spoiled it. And I'll talk a little bit later about how von Neumann spoiled it. In our modern terms, we think of this as a lot like a data flow machine. Essentially what happens is every time one unit finishes an operation, it sends out a signal. And that signal then is used to trigger the next operation. And when you're laying out your program, you are basically creating this sequence of signals from one unit to another that sequences the operations in your program. That actually is pretty much a current thing. We don't think about it that way when we're writing code, but if you look at what the designers at a place like Intel are doing with the CPUs, a modern CPU is basically a big, hairy data flow machine that's implementing, externally visibly, an instruction set. And as we'll see, the Eniac actually did that. So in many ways, we've come full circle. And we're right back to building machines just like we built the Eniac. So in order to do all of this, there's this master clock, and it generates all these signals. Now I'm going to just kind of highlight a few bits of it. Up here, this top signal that has one pulse through this period, this is the one that initiates each operation. So all of those signals that say, hey, I've finished an operation, start a new operation, they're all synchronized to this pulse right here that's called the central programming pulse. By the way, this chart represents one of what's referred to as an addition time. It's 1/5000th of a second. So you've got 200 microseconds here. These two rows have 10 and 9 pulses respectively, and as we'll see in a minute, that's how we read data out of accumulators. It's a very clever mechanism. These next several are how you construct a number from scratch. In the card reader, for example, in the multiple places where we need to construct a digit just from scratch. And so by combinations of these 1p, 2p, 2'p, and 4p signals, we can make any value from 0 to 9. And that is to have that one extra thing that you add when you're doing 10's complement. Think back to your 2's complement lessons. It's 1's complement and you add 1. 10's complement's the same way. It's 9's complement and you add 1. This little pulse right here is the add 1. The long signal right here, that's basically turning on the mechanisms to process all the carries. So as it's accumulating stuff, of course, anytime you've got a digit that goes from 9 back to 0, you set a carry. And then at the end of the cycle, all the carries propagate through. And of course, they may ripple through all 10 digits. And so that's what this longer signal is here. And then the last one is some reset pulses. So this is kind of what's going on in each step. And If you come over to the exhibit, I'll show you actually kind of what's happening as it's going. I've got an LED-based setup that will sort of show you what these things look like while it's running, and you can single-step these operations. The accumulator itself, it has 10 digits and a sign. You might think, however, that would mean that it's operating in sign magnitude. It's not. It's kind of a weird combination of sign and tens complement. So a negative number has both an M for the sign value and the digits are in tens complement. So you get the full range of 10-digit values, both positive and negative. As I mentioned, the inputs cause it to add to the current value. There are 5 possible inputs that you can receive on, labeled by the first 5 letters of the Greek alphabet. We've got 2 outputs, one called A and one called S. Now, when you're outputting, the value currently in the accumulator goes out the A connection. The complement of it goes out the S connection. And you can, by the control switch, determine whether you're outputting on A, outputting on S, or on both. And those are among the operations that you've got here, including the inputs. You can kind of see the highlight. So we've got the different inputs. So I can say, in any given operation I'm going to perform, I'm going to input on this one, say the gamma input, or I'm going to output on A. And of course, every computer needs a no-op. So you have a no-op for every accumulator program position. That turns out to actually be kind of handy. It's the most convenient way to clear an accumulator. There's another switch called the clear correct switch. If you're doing an output or you're doing the no-op, then it clears the accumulator at the end of the operation. If you're doing an input, then this switch causes it to add an extra 1 itself. Now, normally if you're receiving a number that's being transmitted as a complement from somewhere else or as a negative number from somewhere else, that extra 1 that has to be added is part of the transmission. But if you're doing something that you've got a special cable, for example, that drops some digits, maybe is shifting the digits left or right some, then you lose that bit, that digit. And this correct switch lets you account for that on the receiving side. That turns out to be a really handy way of incrementing a value. You just have it take an input from an input that doesn't have anything plugged into it, so it's going to add 0, turn on the correct, and you get that 1. So that's a very convenient way of incrementing things. There are 12 different programs that you can select. Their term program is a little closer to our notion of an instruction. But essentially, there's 12 inputs that can trigger an operation. And then you can select which operation for each of the 12. For the ones numbered 5 through 12, I've also got a repeat count. In other words, I can say, I'm transmitting this, but I'm going to transmit it 3 times. And the receiving end can be set to receive 3 times. Now, when you do that, effectively what you've done is you've added 3 times the value of the first accumulator to the second. So multiplication by small integer constants, you didn't have to go through the multiplier. You could do it right there as part of the mechanism of the accumulators directly. And that was frequently done. And we'll use that in our example here in a few minutes. So here's the how you read it from the accumulator. It's really kind of clever. So I said there was a trail of 10 pulses and one of 9. So the 10 pulses get fed into the accumulator we're reading from. Now, if you think about it, for any digit, if I get 10 pulses, I'm going to go around back to where I started. Somewhere in that process, I'm going to go from 9 to 0, at which point I set the carry. Now, in between these 10 pulses, I've got 9 pulses. Now these are going to be the data that are transmitted to another accumulator. Now here's the clever part. Until I set the carry by going from 9 back to 0, the 9 pulses are going to go out the subtract side, the complement. As soon as I set the carry, the switch flips and they start going out the A side, the additive side. And if you sort of sit down and work through it, you'll realize that what's going to happen then is, if this accumulator digit has the value n, then n pulses are going to come out A, and 9 minus n pulses are going to come out S. And that's how we transmit the value and the complement at the same time. More of that parallelism. We can do adds and subtracts at the same time. The master programmer is basically a very big nested loop machine. You can essentially program it with all your for loops. Now, you can do a little bit more with it than just that, but that's a good kind of first approximation to think about. So there are 10 stage counters in it. So essentially there are 10 things that once you cross a threshold, you can go to the next stage of something. So you could have a sequence of loops that are up to 6 in the sequence. And then there are 10 of those sequences that you can have. There are a total of 20 decade counters that are used to count the limits. That is, how far do I go, how many iterations of this loop before I move on to the next stage. And there's a little bit of flexibility with respect to which of the stage counters a given decade counter is associated with. So you've got quite a bit of flexibility there. But the usual kind of way of thinking about it is, I want something that's executed 1,000 times. I'll dial in 1,000 on this number. I will plug it up so that as long as I'm in this stage that's counting the 1,000, that pulse will cause whatever it was I want to happen 1,000 times. And then, of course, once that's finished, it starts kicking out pulses on another stage that will drive another part of the algorithm. So I can construct these fairly complex nested loop things because, of course, some of the actions that those stages can do is trigger other loops. Another thing I can do is I can actually feed directly into those stage settings information about previous calculations. And this gives me the capability of conditional branching. Now, this is the thing that really made the Eniac unique. Up until that point in time, no machines could really do conditional branching. The Mark I at Harvard could do repetition in sort of the most direct way you can imagine. They took this strip of paper tape, they ran around, taped it together, and they created a literal loop. And that's how it did repetition. But it didn't have conditional branching. Now, I've been told, well, I've read anyway, though I haven't studied the details of this myself, it's possible Zusa might have had some form of conditional branching in his machines, but remember, his were driven by similar tapes. So if you're going to conditionally branch on a paper tape, you still have to read all of the instructions in between where you are and what you're skipping over. So it's not all that effective, a form of conditional branch, if he even had it. But the Eniac did have it. You could, without any delay, choose one of two courses of action based on various things. One of the common ones was the sign of the output. If it's negative or non-negative. If it's negative, I'll take one course of action. If it's non-negative, I'll take another. Turns out the way we do that is we just take the sign bit of a number and plug it into the control signal for the stage counter. All the signals were of a standardized size. They were standardized voltage and shape. that meant that you could use data signals as control signals. And with that ability, you could then construct these more complex operations like conditional branching. One of my favorite ones is feeding a digit in. So you've got this 6-stage counter. If you've got a digit that's anywhere from 0 to 5, then basically it will select one of those 6 outputs. And now you've got like a big switch statement. Or you could think of that as creating an index into an array. You couldn't have very big arrays. Remember, you've only got 20 variables. But you could have a few accumulators in the form of an array and select the element of the array in this way. So let's take an example. Now, this is an example that comes from the demonstration that was performed at the unveiling of the machine. So we said this is the 75th anniversary. In February of 1946, February 15th, they did the unveiling, announcing it to the public. As part of that, they did a big demonstration of the machine. A number of different computations were performed, and they had small groups coming in to the machine room. They would run the demonstration for them. People would ask questions. They would rerun parts of it. And then the next group would come in, and you had most of the day was spent doing this. One of the elements of the demonstration was computing a table of squares and cubes. And we're doing it not by multiplication. We're going to use math to do it a little faster and more easily. We're going to use a good old rule that you probably remember from high school, or you may look at it and go, oh yeah, I think I saw that in high school. I haven't thought about that in years. X squared is, x plus 1 squared is x squared plus 2x plus 1. And x plus 1 cubed is x cubed plus 3x squared plus 3x plus 1. You go, oh yeah, Pascal's triangle. Yeah, that's what we're looking at here. Now, the beauty of this is, it says if I know the current value of x, x squared, and x cubed, I can get the values of x plus 1 squared, and x plus 1 cubed by just doing some additions and multiplying by small integer constants. And remember, multiplying by small integer constants is very easy. I just use the repeat switch. So we're going to do this calculation. We're going to generate 100 values, and we're going to punch them out to cards. And in the original demonstration, they took those cards that were punched and then took them to punch card equipment, which printed out a table on paper. And that piece of paper, they made a bunch of copies of that piece of paper, and that was part of the press release packet. There had actually been a press version of the demonstration 2 weeks earlier. It was a little different than the one done in the real unveiling. And so the reporters, what got reported in the newspapers, keep in mind the reporters were not there at the real unveiling. So they were describing what they had seen in the press version of it. It was a little bit different when it came to the real thing. But this was part of both, at least as far as we can tell. The records are a little sketchy, but we're pretty sure this was part of both. So what we're going to do is we're going to store x in accumulator 15, x squared in accumulator 16, and x cubed in accumulator 18. And I'm going to call x squared y, x cubed z, so that as we're going through the algorithm talking about how we're modifying the values of things, it won't look funny to say, I'm going to modify x cubed by this amount. Well, yeah, I am, but I'm not changing it quite the same way I would think of mathematically. And all these are initially 0. So we're going to start out saying that 0 squared and 0 cubed are 0. That's good. We got that much right. And then we're going to go through these updates and punch out a card for each one. So What's the algorithm going to look like? Something kind of like this. Well, I need to add 3x squared to the x cubed here, so that's going to be adding 3y to z. So this addition right here in the second equation is our A step. Our B step is this addition that follows it, where I'm adding 3x to it. Then step C is this addition in the first equation, where I'm adding 2x to the x squared. And then I need to add the 1's, both to y, z, and to x. And so those are steps D, E, and F. And then once I've got the data updated, I just punch the card. So far this looks a lot like what you would do if you were to sit down and write a program to do this in a modern language. You would probably have statements that look very much like that pseudocode there. Now, as I said, we can take advantage of some parallelism. And there are several places we can do that. In particular, you'll notice that in steps B and C, both of those involve transmitting the x value some number of times. Well, maybe I could do those then at the same time. If I'm already transmitting it 3 times, I can have one accumulator receiving it 3 times, and I can have one of them actually only receive twice and ignore the third one. So I'm transmitting it 3 times. One is receiving 3 times the value, one is receiving 2 times the value. So I can combine steps B and C into one. Similarly, I can do all of these increments adds of 1 in parallel. I don't have to separate those out as separate steps. So let's put that parallelism in, and now we've got a little bit more compact algorithm that takes advantage of the fact that this machine can do more than just a conventional sequential instruction set. We actually have the capacity to do things in parallel. So now the next step of our programming, usually we would kind of think in terms of the sequencing of operations as being the sequence of our steps, our source code statements. Remember, in the Eniac, because it's a data flow machine, the sequence is determined by these pulses that get transmitted from one place to another. So what we're going to do is, for each of these statements that we've got written here, we're going to assign a control signal to it. And the idea is that when that control signal gets a pulse, whatever happens in that statement starts. When it finishes, it generates the pulse for the next statement. And I've labeled it with some pulses. Now, these are referencing the trunks. If you see over here, kind of in this little corner right there, that area in the bottom are trays with 11 connectors. And those go all the way around the machine. So if I want to transmit a pulse from this accumulator to this other accumulator over here, I can feed the pulse into one of these trays and then pull it back out at the other end. And these numbers are referring to which tray and which connector on the tray. I'm not required to make this sequential. I can skip over numbers. That'll sound real familiar to basic programmers. We all got used early on to skipping 10 for every one of our statements, so we could come back and fill in some statements. And you end up with all these areas that had the statements separated by 10, and then you had this one block right here where you suddenly needed 15. And it's like, I got to change the numbers. At least there, the numbers were all monotonically increasing. They don't have to here. They can be any numbers you want. But for the sanity of the programmer, it's kind of nice to go ahead and allocate them sequentially as you go. So as you can see here, I've mostly done that. There's a few places that it's not quite, like I skip over 2-2, and I jump from tray 1 into tray 2, but there are reasons for that in the bigger picture. So this is what we're going to wire up on the machine. We're going to set all the switches to do these operations, and we're going to wire up these control connections here. And the way that looks is this. Now, These are the diagrams that they would use to determine how to wire the machine and how to set all the switches. We're going to zoom in on this a little bit in a moment. But this particular section of it is showing what's happening with accumulators 15, 16, and 18 and the master programmer for the whole of the demonstration. I've grayed out the parts that aren't relevant to this particular part of the computation, this particular sub-piece of the demonstration. So the darker black lines are the ones that indicate what we're doing according to that algorithm, and then these switch settings are that way as well. Before I zoom in, let me just say a little bit about what's going on over here with the master programmer and the initiating unit. We've got this first line 1, 1. You remember that line was what labeled the loop in our algorithm. Well, that's feeding into the first of those stage counters, and it's generating a pulse coming out of that on line 1, 3. This part of it means I'm in the phase of the demonstration that includes the squares and cubes. There are several kind of blocks of functions that are demonstrated, and one block includes the squares and cubes. And so that's what this little piece is simply indicating. So we get a signal on line 1, 3 for that. This then is going into the second of those stages. It is the one called B. And so here's our count of 100. So we're going to have 100 iterations of this. And as long as we're still in that set of 100, then every time we get an input there, we'll get an output that's connected down here to the line 2, 1. And you remember 2, 1 was the first part of the body of our loop. When we do the punching, that happens down here with the signal 2, 5. That sends a signal up into here that initiates the punch operation. But because the card punch takes 0.6 of a second per card, we might have to wait on it. And so this signal right beside it is the output that says, the punch is now ready for some more information. And we use that to trigger the next iteration of the loop. So that's what's happening over here kind of in the control side of it. I'm going to very quickly say something about what happens in the data side of it by zooming in on this. Okay, so let's take the first step, the one on 2, 1. It's initiating an operation right here. It's also initiating an operation right here. This one, accumulator 16, remember that is our x squared value. And we're going to transmit it on the A terminal. So we're going to transmit the value, not the complement, 3 times. Accumulator 18 is calculating the cubes. It's receiving it 3 times. And this connection up here is how the data is transmitted from 16 to 18. This terminal right here is where it sends a pulse when it's finished with that operation. And so that's triggering the operation we labeled 2, 3. And if you follow 2, 3, you'll see that it causes this one to transmit 3 times, this one to receive 2 times, and this one to receive 3 times. And we just keep sequencing through those operations. These right here, they're labeled epsilon. Not sure how well you can see it at a distance. But the ones that have an epsilon and a little x up in this top switch, those are the ones that are doing the increment. It's saying to receive on the epsilon input, which has nothing connected. So that means I would add 0. But that X indicates the clear correct switch is set. And that tells us then we get added an extra 1. This is all it takes to do that computation. And we get the whole table of squares and cubes that way. Now, I want to demonstrate all of this. And I'm going to run through the demonstration as we've reconstructed it that we believe was done on February 15, 1946. So the first step of this was to read some constants off of a punch card. And we loaded those into an accumulator. Now, you may not see it very well, but we loaded a constant into this one. So let's look at that. This is the constant that we loaded. Each column is 1 decimal digit, and the position of the orange dot, there were neon lamps, is the value of that digit. It's not real easy to see. If you've ever worked with neon lights, you're just pretty accurate in that regard. So this has the number 97,467. Now what we're going to do is add it to the second accumulator 5,000 times. Now this is actually in this simulation running a little slower than the real machine. The real machine would do this in 1 second. Remember I said that the addition time was 1/5000th of a second. So it could, it's always quoted, it can do 5,000 additions per second. But with the parallelism, you can actually get more. But in this case, we're just doing 5,000 sequentially, and we get a sum here. Now the next step of the demonstration I'm not going to do. They took the machine and they changed the clock to slow it down by a factor of 1,000 to show you what it was like compared to the fastest machine that was available before this. And then they started this same operation. Now, there's no way they let it finish because it would take 16 2/3 minutes. I'm not going to even waste your time with that. I'm just going to move on to the next phase. So now we're going to demonstrate the multiplier. The thing we're going to do is load a number into these two accumulators back here. These are the multiplier and the multiplicand. And the product gets formed in this set of 4 accumulators over here, where the final product appears in the last 2. So if we multiply it once, well, we got an answer right here. Simple enough. Let's zoom in and multiply it another 499 times so that we get it 500 times that product. And that's it. The fact that it can do several hundred multiplications per second turned out to be what caught von Neumann's interest. In 1944, while the machine was under construction, Hermann Goldstein, who was the Army liaison to the project, bumped into von Neumann at a train station and said, hey, I'm working on this machine and it can do several hundred multiplications a second. And that suddenly got von Neumann's interest because he was worried about doing calculations for the Manhattan Project. And nothing they had could do calculations nearly that fast. So he became very interested in the project at that point. Okay, so this is it now doing our squares and cubes is the next phase of our operation. And in the little window on the bottom right, this is the punch card output, where we've got x squared, and x cubed being printed out. You'll notice that everything is happening kind of that's because it has to wait the card punch. Most of the time, those lights up there are just sitting still, indicating that to wait the 6. At 0.6 of a second per card, 100 cards, exactly 1 minute. And so we are now about 4/5 of the way through our minute, rapidly getting to the end. So with just a few more seconds left, we will finish up this print of 100 squares and cubes. Now the next thing they did was they said, let's run the same calculation, but without the printing, so you can see how it really calculates. Watch carefully. That's it. In the write-up that we found that describes the event as it was demonstrated in the press event on the 1st of February, Arthur Burks, who wrote that up, he says, this part of the demo, some people missed because they were still writing in their notepads. That's why I said look carefully. Now, the next thing I'm going to calculate is a table of sines and cosines. This is being solved by a pair of simple differential equations, and we're looking at time steps, or in this case, steps of angles, that are just small steps in calculating an update to both the sine and the cosine. This illustrates the type of problem that originally motivated the creation of the Eniac, solving differential equations. Now, if you've taken a differential equations class, you learn lots of tricks for getting closed form solutions to things. Those are all special cases. Those aren't the cases that describe the real world. Typically, when you're working with the real world, the equations do not have closed form solutions. And you end up having to solve them numerically. Up until this machine, the way that was done was with computers. Except at that time, the word computer was a job title. Had armies of people with good old-fashioned desk calculators, carrying out repeated additions, occasional multiplications. In fact, that's kind of what inspired the structure of this machine. I want to build a whole bunch of adding machines that can all feed numbers into each other. So the next part of the demo is an example of the type of problem that doesn't have a closed form solution, and that in fact was so necessary that the Army was willing to pay for building the machine as a result. Now, this isn't the only thing the machine was built for. Some authors have been somewhat mistaken by saying it was a special purpose machine just for this. If you read the actual stuff that was being written at the time it was being developed, they are very clear that they want a very general purpose machine from day one. It is currently now calculating the trajectory of an artillery shell. Now you may think, wait a minute, I learned in high school that that was just a parabola. If you're in a vacuum, yeah. Air resistance makes it not a parabola. And in fact, it doesn't have a closed form solution, especially because I mentioned, remember, air resistance is this weird function that is an analytic. So in order to simulate the flight of a shell, you have to break it down into small time steps and look at how the velocity and position in both the x and the y directions change at each time step. And it was those hundreds of manual calculations that people were doing that they wanted to replace with this machine. And the Army said, there's a war on, this will save us a tremendous amount of time and effort. Yes, you can have the money. The fact that it actually ended up getting finished after the war, well, that's that. But interestingly, the first application of it then was for Los Alamos in atomic bomb design. So this simulated the flight of a shell that lasted, well, it hit the ground between the 28th and 29th second. Again, my simulation is running slightly slower than the original, but in the original machine, that particular simulation would run in about 20 seconds. So they were extremely proud of the fact that in demonstrating this to other scientists, to the Army brass, this could calculate the trajectory faster than the shell itself actually flew. And that was a big deal. All right. Very quickly, I want to mention one more thing about the programming of this. This form of programming wasn't the only way it was used. It turns out if you've got a data flow machine that is Turing complete, basically you can repeat and have conditionals, you could design a program on this thing that would interpret instructions, i.e. you could make a CPU. And that's what they did in 1948. And from early 1948 until its retirement in 1955, the bulk of its use was done in that way. And to do that, they read those constants, the instructions, off of the same function panels that would also hold things like logarithms or error resistance coefficients. And that's how it was done for most of its life. The last thing I'll mention before opening the floor is there was a wonderful story about preparing that demonstration. The two programmers who were working on it, Gene Jennings at the time, later Bartik, and Betty Snyder at the time and later Holberton, were the two programmers who were doing this. On February 14th, Valentine's night, they were in the lab trying to get the last bug out of their programming. The machine would calculate the trajectory perfectly, but the shell didn't stop when it hit the ground. It kept going. Now, the train was leaving, and so they had to leave for the night. The thought was, if we can't figure it out in the morning, we'll just stop the computation and kind of talk our way around it. But remember, this has the capability of doing conditional stuff. And so you'd like to demonstrate that by having it actually stop when it hits the ground. So Jean goes to her apartment, Betty goes to hers, come back the next morning, and Betty's been thinking about this overnight. And she comes in the next morning, walks over to the machine, walks up to the panel, takes one switch, moves it one position, and then it all works. Jean has been quoted as saying that Betty can do more debugging in her sleep than anyone else can do awake. And Betty, by the way, is responsible for the technique that we still today call breakpoints. All right, we have just a few minutes left. Are there any questions?
Let me go around with the mic, so raise your hand and then I'll find it. Yeah, you mentioned they were able to swap modules out when there were failures, but how did they know a failure occurred? Was there some kind of checking?
There wasn't a checking mechanism directly built into the machine. They had several techniques. One was when you would first kind of start up a day of operation, there were certain procedures you'd run through to kind of check the machine, make sure you were getting the right results. Another common technique was, let's say I'm doing something like calculations. What I might do is do 5 trajectories and then stick in some inputs that produce a known output. Then, as I'm going through my output, as long as those periodic ones are showing the number that I expect, I can believe it's working in between. But if I hit one of those that doesn't, then I know I've got a problem and I can go track it down. Now, they also had a handheld control unit that would allow them to single-step the machine. And so you could walk around the room, single steps, and if a column in one of the accumulators was showing either no lights or more than one light, you knew that digit was bad. If an operation just shooting up to some point and just didn't happen, the of that unit. So it wasn't quite as bad as you might guess in terms of, oh, I've got to check 18,000 tubes and figure out which one's bad. But the machine didn't have like an alarm panel that said there's a fault in the multiplier.
Thank you.
You're welcome. Any other questions?
Was any useful work done before the public demonstration or during the war?
Yes. Well, there was some done between the war and the public demonstration. In the winter of 45-46, the dates are a little unclear, but it seems like it was mostly during December. A team from Los Alamos came out to Philadelphia and did some computations on the machine. It was all completely classified at the time. Nobody working on the project had clearance to know what the calculations were. We now know what those calculations were. There was a going on at the time with regard to the weapon that we know as the hydrogen bomb. They often called it the super. Teller, of course, was a big proponent of this weapon. But there was a really core question about how you could ignite it. And it wasn't something it could solve analytically. So they programmed up some simulations and ran them on the Eniac to help settle the question of whether the approach to ignition that they were considering would work or not. Now, what's interesting is that set of wiring switch settings was still on the machine when the press demonstration was done in February. So they're demonstrating these, basic operations, and then they say, now to demonstrate the more complex capabilities of the machine, we have this calculation being done. We can't tell you what it is. And as you can imagine, as far as the demo goes, that kind of hit with a dull thud. And that's why they said, what we really ought to do is put something on it that people can understand. So that's when they decided to put the artillery trajectory calculation on it. And Snyder were working on that in that 2-week period between the press demonstration and the unveiling. And so what the press saw didn't include that. But when Army people who were experts in trajectories saw this, they could watch on the panels, and they could watch as the lights were going up in altitude, and then as soon as the velocity turned negative, they could see the numbers coming back down. And they thought that was the coolest thing in the world. They had them read over and over again that day. Interestingly, right after all of that, Manhattan Project people came back in, took the machine back over, and kept doing some more calculations on it. I mentioned that it had been sort of switched into a sequential instruction set mode at one point. Well, it turns out the first program run on it in that mode was also for Los Alamos. And it was the birth of techniques that we know as Monte Carlo techniques, where they were simulating basically the exponential growth of neutrons in a chain reaction. And because of the limited storage capability of the machine, at each generation, they called them clicks, they would only take a sampling of the newly generated neutrons and follow them into the next step. But that's how they were doing that kind of work. And before that, Los Alamos only had punch card equipment to work with. And so this was a big, big boon for them. As I mentioned, number theoretic work was done on it. Supersonic airflow calculations were done on it. And yes, trajectory calculations that had justified the funding did get done on it some. But there were lots of other applications. Yeah.
Then moved to Aberdeen Proving Grounds?
That's right. That was done, so in about the fall of '46, they shut it down to prepare for the move. By early '47, it had been reinstalled in Aberdeen and was up and running, sort of. I say sort of because one of the ways of keeping the tubes from burning out was you never turn off the heaters. So the machine actually has controls on it that control the low voltage supply for the heaters, the rest of the machine. And the operating procedure that the designers had laid down was you never turn off the heaters unless you have a major fault that has to be dealt with. Well, not long before it got moved, somebody had defeated certain thermal interlocks and there had been a fire. The Army's reaction to there being a fire is, clearly we must turn it off every night. So it gets to Aberdeen and they start turning it off every night. And there's just no reliability. And word finally gets back to the people at Penn. It's like, don't do that. Leave the heaters on. It will be much more reliable if you do that. But it was moved. In fact, they had prepared a special room for it. And it was one of the few rooms in the area with air conditioning. Turns out later in the machine's life, people used to drag their desks into the room during the summer since it was the only room with air conditioning. I think we had another question back here.
Yeah, yes, you mentioned von Neumann. So was there any influence from either this Penn machine to Princeton or vice versa?
Yes. Now, this is a whole other part of the story that I didn't really get into yet. But it looks like we've got a little bit of time. I don't see Bill here, so. So I said that von Neumann got interested in things in 1944. By this point, the Eniac team was beginning to work on their next machine called the EDVAC. And the core there was, can we come up with a way of having something that will store more data? Because our big limitation here is how much data we store. And they realized in that process that if I can store enough numbers, then I can eliminate the time consumed with the switches and wires by storing the numbers in the memory. So they were developing the Eniac concepts based on that, the EDVAC concepts. So we see the first indications of that in January of 1944. By the time security clearances and all are done and von Neumann can actually visit Penn, it's August of 44. So they're pretty well established in understanding how to build a computer that we would recognize as a stored program computer by this point. Von Neumann joins the group and begins attending the meetings. Now, here's what I believe happened. I'm not inside von Neumann's head, so I can't say this is exactly what happened. But von Neumann had known Alan Turing beforehand. Remember, von Neumann was at the Institute for Advanced Study. At this time, the Institute for Advanced Study is housed in the same building as the Princeton Mathematics Department. Some years earlier, Turing had done his PhD at Princeton. So von Neumann and Turing knew each other. And I believe what happened is when von Neumann gets there, he sees the ideas that Eckert and Moseley are working on. And he realizes what they're talking about could be a realization of the universal machine that Turing theorized. If we get all the instruction set right. If we get the right set of instructions, maybe it could be this universal machine. And if you read through what people have to say about von Neumann's involvement, they always talk about how he was really focused on the instruction set. So as part of this, and in his own kind of process of solidifying these ideas, he wrote what he called the first draft of a report on the EDVAC. There was never anything other than the first draft. But copies of this got disseminated across the world and created a lot of excitement. So in the summer of 46, Penn hosted a summer school where people came to learn about these ideas for building a computer. So you had people from Manchester in England, Cambridge, Harvard, MIT, every place we know of that had an early computer project had somebody attending this summer school where they learned about these ideas that had evolved out of the Eniac project and summarized in his first draft report on the EDVAC. And that same group then goes out from there and creates all these initial computer projects that we all know about, like the SSEM or the Baby at Manchester, the EDSAC at Cambridge, the Harvard Mark II. Well, Mark II was already under construction at that point, but Mark II and Mark III were influenced by this. The Whirlwind. The Whirlwind project was originally going to be an analog machine. And after this conference, they said, clearly the right way to go is digital. And they completely started over again to build a stored program machine. So this is kind of where it's all born. And it is through this interplay between the Eniac team and von Neumann that the word gets out. And of course, the IAS machine then was the evolution of that work. Now, one of the interesting things is if you read through the early reports on the IAS machine, there's one of them that includes a statement that sort of is to the effect of, now that we understand, almost anything will accomplish universality, our focus has been on performance. So I really think that, in the interim, von Neumann was kind of justifying to himself, essentially coming up with a proof and realizing it wasn't interesting enough to publish, that if you've got looping and conditional branching, then you've got universality. And as I said, that's what the Eniac had. Now, he did have one other part to play in this, and this has to do with that quote from Lemmer about von Neumann spoiling it. That conversion of operating technique to what is essentially like a stored program type model, von Neumann was very supportive of that effort. He played a part in it, helped kind of spark the interest in doing so, and his wife was also very heavily involved with coming up with the details of that. And I kind of have a suspicion that he saw that, let's modify Eniac to be this instruction set processor, as kind of a test bed for his ideas on the IAS machine. I have a feeling he kind of thought of it that way. I've never seen anything to say he definitely did, but I kind of have a feeling that's what he thought. Unfortunately, the history goes kind of pear-shaped from there. There's a lot of bad feelings floating around. There's a lot of who's taking credit for what, who really did what, and it all gets really ugly when there ends up being a patent trial. But at least the actual genesis of these ideas and how they got disseminated, I think most of us at this point have a pretty clear sense that they did indeed originate with the Eniac team, that von Neumann recognized it, was able to sort of capture it in a way that could be clearly described and explained, and he may well have contributed some to it, but the core ideas were there already by the time he got involved. And then that's where it all came from. So, any other questions?
I don't think we have time for more. You've got an exhibit, right? So
Yes. Yeah, feel free to drop by my exhibit, but thanks again for coming out, and you've been a great audience.